I want to talk about springs, and I'm just going to start with a couple of equations that you're going to see. So you all know what a spring is. A spring can be stretched out. Some kinds of springs you can compress depending on the kind of spring it is. So if you look at the spring inside a pen, for example, that's one that's able to compress a little bit. You can stretch it. So you can either elongate it by pulling it out or push it together by compressing it. And so as you compress a spring, it takes force to compress a spring, and the spring pushes back on you, and that is called the spring force. So there is a spring force, F with a little s, F sub s, and that is equal to kx. And k represents a spring constant. Every spring is a little bit different. So if you could measure the strength of a spring and put it into a number, that's what the spring constant represents. Some springs that are much tougher to move, those have a bigger spring constant. Some springs are very easy to elongate, for example, they have a small spring constant. The other thing that you're going to see is x, where x is the change in length of a spring. It turns out that it doesn't depend on how long the spring is, it just depends on how much the length changes, and it's really from equilibrium. And equilibrium here means the balanced state. So if I look at this little spring here, I don't know how you can see it, the natural state of this is to have a certain length. So if I could compress it, I could measure the change in length, and that change in length would tell me what x is. And because it's a length, we're going to do it in meters m. Now, these same variables can actually be used also to figure out the potential energy of a spring. We can say the potential energy of a spring is 1/2 kx squared. So you'll see that force in x has a linear relationship, but potential energy in x has an exponential relationship that goes with the x squared. I'm going to give you an example right here. So let's say a spring is naturally 0.1 meters long. That's 10 centimeters about this long. But you add a weight to it, and that weight increases the length to 0.15 meters, meaning it gets 5 centimeters longer. So the change in length, x is the change in length, so it would be 0.15 meters minus 0.1 meter. So the length changes by 0.05 meters. That's how you get x. Now, I didn't tell you the spring constant here, so we can't figure out the force. But let's say that we know this weight has a weight of, let's say, 20 newtons, right? 2 kilograms, about 4 pounds. So if it has a weight of 20 newtons, what it's telling you is that that weight is pulling down on the spring with 20 newtons of force, and by Newton's third law, action-reaction, the spring must be pulling up with 20 newtons of force. So we get force is 20 newtons, equal and opposite to the weight, and that has got to equal k times x. So you get 20 newtons equals your spring constant times 0.05 meters. And so if we solve for k, 20 newtons divided by 0.05 meters, divided by 0.05, put this in the calculator, I find that the spring constant here is 400 newtons per meter. Let's say I want to find the kinetic energy of this. I'm sorry, the potential energy of this. The potential energy is 1/2 kx squared, so 1/2 times, we figured out that the spring constant is 400 newtons per meter. We know that the stretch elongation is 0.05 meters. And we got to make sure we square this. So you get 100 times, 1/2 times 400 is 200. That's times 0.05 squared. So you end up getting a potential energy of 50 joules. And you can do this for all sorts of springs. Sometimes you might see something where you're given the potential energy and you have to work backwards. So maybe you get the potential energy and you need to find the spring constant. So you start with, hey, I know PE and I know X, and I need to find the force. Well, I can't find the force until I find the spring constant, so I can say, I know X, I know K is got to be 2 times potential energy divided by X squared. I get K, now I know K and X, and I can solve for force. Either way, sometimes you will see this expressed as a negative Kx. And this is all related to what's called Hooke's law. So this equation right here, force equals Kx, is Hooke's law. And the negative sign is put in there just to show that this force is what's known as a restoring force. And a restoring force is there because it tries to restore equilibrium to the spring. So the spring always wants to return to its natural equilibrium state. It can't always do that, but that's what it's trying to do. And so the force is always in the opposite direction as the stretch. So if you take your spring and you make it longer, the force is going to try to pull it shorter. If you compress your spring, the force is going to try to make it longer. It's all bouncing around in equilibrium. And what happens is, imagine you had this on a spring like that, and you could actually pull it down, and it would be bouncing up and down and up and down and up and down. So it's oscillating almost like a pendulum would oscillate. And what you'd find is that the spring energy, let's see if this is the top. This is the middle. And this is the bottom. And it would be going up and down and up and down and up and down and up and down. At the middle, it would be at its natural length. So in this case, it's at its equilibrium length, so x equals 0. And because x equals 0, the spring force would equal 0, and the potential energy of the spring would also equal 0 if x is 0. The problem with it is it can't stay in equilibrium. So if you put it here and you don't give it any velocity, it would just sit comfortably at that length. But as soon as it had velocity, it would go past the equilibrium point until it keeps going, 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 going. And as it goes down, the force increases, trying to pull it back to the equilibrium point. And as the force increases, the spring potential energy increases as well. And so at this point, potential energy of the spring has increased. Potential energy due to gravity is at a minimum, just because it's the lowest. But the total energy has got to stay constant, remember? So this has a bunch of spring potential energy right there. This right here has a lot of kinetic energy is max because velocity is max. But here, kinetic energy is 0 because your velocity is 0. At the top, similarly, velocity is 0. Potential energy due to gravity is a max. Potential energy due to the spring is high. Kinetic energy is equal to 0. So in something like this, you still have energy transformations going on as the spring oscillates up and down, always trying to reach that equilibrium point, but not being able to stay there because it has enough velocity to carry it past equilibrium. That wraps up my talk about springs. Thank you very much for watching.